Hello everybody, we have a problem in basic quantum mechanics here to solve. This problem appeared in a GRE exam. In this problem, the wave function for a particle constrained to move in one dimension is shown in the graph shown here by this strange looking wave function psi, where psi is equal to 0 for x less than or equal to 0 and psi is also equal to 0 for x greater than or equal to 5, and we are asked here what should be the probability that the particle would be found between the points x is equal to 2 and x is equal to 4, and our answer should match one of these 5 answers: A, B, C, D and E. In order to solve this problem, the first thing to note is this. In quantum mechanics, a particle or any physical system is always defined by a normalized wave function, psi n, say, psi n. And this normalized wave function is such that it makes this integral psi n modulus square dx equal to 1. And we call this integral as the total probability, Et. And of course, the total probability should be equal to 1. Here in this integration, the limits of integration are those limits on which the wave function is defined. And we take the modulus square of psi n because sometimes the wave function is a complex number and we need a positive definite number to define probability. The second thing to note is when you are given some function, say f of x, and you plot that function, say this is your x-axis and this is your y-axis for f of x, and you plot that function, say from here to here. These are the limits over which the function is defined. So the integral, this integral f of x dx, and the limits of integration are from here to here, the given limits over which the function is defined. This gives you the area under this function. This is very well known fact. Similarly, if you plot psi n modulus square, the area under the function psi n modulus square will be defined by this integral, which should be equal to 1. That is the total probability. In other words, the total probability is the area under the curve psi n modulus square. Now, in our case, I have plotted here on the right the function psi squared in the given region in which psi is defined. Luckily, instead of the integration process, the area under the curve psi squared can be easily computed in terms of the areas of the squares. Now, if you count, the total number of squares under the function psi squared is 16. This suggests if we assign an area of 1 by 16 to each square, this will make the total area under the curve psi squared equal to 1, and this will also make the total probability equal to 1. By requiring each small square to have an area of 1 by 16, we actually have normalized the wave function. And now we should choose on the y-axis or on the psi squared axis each unit to be 1 by 16. That will make the area of each small square to be 1 by 16. So this is 2 by 16 now. This is 3 by 16. And so on. you can always choose your own scale, whatever you like on any axis. You have that freedom. Now you are almost there. Just count the number of squares between the points x is equal to 2 and x is equal to 4 under the function size squared, and that will give you the area or the probability of finding the particle between the points x is equal to 2 and x is equal to 4. So how many are these squares? 1, 2, 3, 4. So 4 times 1 by 16. Each square has an area of 1 by 16. Plus, how much are these? 1, 2, 3, 4, 5, 6, 7, 8, 9. These are 9. So 9 times 1 by 16. So how much is the total area now? This makes it 13 by 16. And this is your answer, E. Thanks for watching, guys.